So in this video I am going to discuss circle diagram of synchronous machine and related issues. So while before we go to circle diagram, let us proceed step by step. Let us first try to understand that what is the function of like armature current. If we consider the armature current as a function of power developed. So I'm talking about motor case, obviously. So as we know that we are considering balanced steady state operation. So during that, if we disregard the constant losses, like I have explained in the video, then per phase power will be something like Vi cos theta minus I square R. Correct. Now, this is the amount of mechanical power developed. Obviously, from this mechanical power, you need to subtract all the other losses, like constant losses, but as they are constant, so we can skip them aside. And from this equation, let me number equation one by one, otherwise we'll get lost because this is going to be a kind of mathematical analysis. We'll do a hell lot of analysis. Now, what we can do here is that we add both sides v to r square. So, therefore, it will become let this be equation say equation 2. Now you can see that here the constant quantity V2 by R we are having, and that this side it is becoming something like a vector addition between like if we take a square root of this, then if you take this square root of this side, it is like a vector that is having a kind of giving you a feel of resultant things, like one side of the vector is v2r, another side is I, and it is giving you the kind of resultant things. Now see that Vy, let us analyze it. Vy2r is what? That is its nature is nature of current, and it is in phase of your supply voltage V and express in ampere. Now that the other term of this equation is that it's like two current. So it's like you are having is you are trying to obtain a kind of triangle sum where it is one side is v by 2r, another side is I. So that is equal to what we are getting is this gentleman root under this. Now if the condition we imposed on P, that P remain constant, then what we will get, do note that as we are considering machine, So what we can understand that V constant, and now we are in addition we are claiming P is also constant. So therefore what it would become like this right hand side will become a constant term. This will become a constant term. This whole things will become a constant term. Right. So if this is constant and this is also constant, but what you are having here is very interesting that it is the diagram of this. I have taken it from the book of S. Langsdorff. Let me write. Here it is the angle. It is the angle theta, and actually they use RA, means you can understand that RA is equal to R. So here you can see that it is very interesting to note you are getting something that kind of circle at a center C. How this circle comes in the picture, let me tell you that this circle center is at a height of V by 2R, that is of current, right? Now this radius is given by this. Now we have already discussed for a constant current you are having this much is constant, V by 2R square minus P. So this becomes the two side of the triangle. Now if we think about changing this, how this can take place, like okay, so first of all try to understand that when the power will become zero, obviously the power will become zero. Let us be very clear that this circle that is centered at O, sorry C, this circle which is centered at C, right? So this circle here is like that. Yeah. So this circle that at center at C, here you can clearly observe that the circle at C, it is actually growing outward. The smallest value of current will become when the radius of the circle will become something that is V, radius of the circle become V by 2RA. And as long as circle radius is small, like even if we can, what is the amount of this circle radius? That radius is given by this term V by 2R square minus PRA. So this is the locus when your power is 0, right? The radius of the circle is given by this. When the power is 0, then you will have this bigger circle, this one. Now if you increase the power, then what would happen? If you increase the power, it will form a concentric circle. Like if I want my power to be, say, I give some value 20. Now for this we can figure out the radius, and that radius will be this radius. Now there is one more question that need to be answered here, that for a given power, what we can see is that this current, this locus of current is varying along this circle. Like for a given power, we can have our current locus at any point on our circle. If you are not getting my point, try to understand that suppose when it is here, then also you can apply the same equation, right? But you will have a different value of theta in this case. Now what is the maximum value of power? P max will be when you will have this, see, the current value cannot become an imaginary number. So the smallest value of current will become when this will become 0. So that gives us the maximum value of power, that is limited by V square by 2RA. Sorry, V square by 4RA. So the current correspond to the maximum power is that V by 2RA, and the power input would then, how much power input will be there? If this is the value of P max we are getting, I become is equal to this, means here, that means your I becomes how much? Okay, first of all tell me what would be happen to the cos theta. So theta will be 0. Now see, what about I? I is equal to V by 2RA. So what about your input power? Input power will be V into V by 2RA into cos 0 is equal to V square by 2RA. So you are giving V square by 2RA and getting the maximum value of V square by 4RA. Now see that V square by 4RA, so is your output, and is your input is V square by 2RA. So what is the efficiency value? That is 50%. When we generally get 50% for maximum power? In network theorem we have read that for maximum power transfer, our efficiency becomes 50%, that we can verify here, right? who consume this additional loss, that is your I square r. If you obtain I square r, you will find that I square r will also become a square by 4 r. Here ra is equal to r, so all this should be r. Actually I am taking this means diagram from the book of Langston, so sometimes I may write r a, but don't get confused, it is r. Okay, so that's all. So okay, well, one thing that we have not yet done clearly, that what we can write is that for all value of current and power we can write it like I is equal to v2 IR cos theta. So this gives us uh, current for a particular power. V and R will remain constant. Now value of current, it clearly indicates that it has a, means this value of cos theta has a huge control over the value of current. So if you make cos theta is equal to 0, then you are going to get like a very high value of current from that. Apparently cos theta is equal to 0 may gives you an impression that your like 0 power means there is like current will become 0. If you put cos theta is equal to 0, you will see that current will become 0, because for that P will also become 0. But uh, can you explain that how it can happen in that way? Like your machine, uh, indeed your machine is operating at uh, means 0 power factor, but its current is also 0. Then how the machine can rotate? Or there is some kind of like logical means fallacy in our description. Otherwise you can see that it holds good, and obviously since it is cos theta, so theta lagging or leading plus or minus won't make much difference. So for different value of like for a value of cos theta you will get current, and that current will be like means since you are expressing it in forms of power, so for a constant power you will have two value of current, and that is quite understandable. Like here if you see that for a particular value of theta, let me show you. Say if we consider then you can see that we can have two lines, and both of them are making theta, right? Well, now let us see that what would happen when we consider it like a function of our armature current as a function of excitation. So, armature current, what we can write is that V is our terminal voltage, V is equal to E plus IZS. If you follow Langsdorff, what Langsdorff did, following the same notion for your means transformer, where we used to represent induced EMF, since this is the kind of EMF in opposition with our means applied voltage. If you recall what we do in case of transformer, we used to represent it by minus E. Let me write the transformer equation. Transformer equation was like uh, so Langsdorff want to follow that same notion, and that is not like logically that is also okay. So you can here use minus E also, right? But whether you use E or minus E, that won't make much difference, because as long as you are like what is inside, logically speaking, it in that, especially if you want to maintain that cogency, it should be minus E. But also if it is a means this minus E whatever, it's not a kind of physical thing inside, like inside your transformer it was quite a physical thing, but this minus E, or in this notion it is trying to mention, it is in our notion it is minus E naught, that is practically means you can never realize this one practically. So that makes almost zero sense, but anyway, uh, now Zs is equal to what? Zs is equal to R plus Jxs is the synchronous impedance, and they have considered it counter EMF. For counter EMF consideration, everything will remain same, only their argument, and that is not a bad argument, that what we draw in case of motor. Okay, motor phasor diagram, I think I having motor phasor diagram. Just a minute. Well, could not able to locate that motor uh, equation. Perhaps I have deleted it. Let me draw it. That is not a big deal. It is V. Then your I is like this at an angle theta. So the standard equation will be what? Minus IR. So minus IR, then minus JIXS. Generally what we do, the line which joined this gentleman, previously we denoted it by eta naught. So what Langstroth suggests that instead of eta naught, you denote it by minus eta naught, right? So there is no harm actually. Like whatever you do, it will remain same. Obviously, for generator, it should not be the case. In case of generator, it should be like eta not be, but as it is like a kind of giving you a feeling of back EMF, or that is acting in opposition of this B, Langsdorff want to maintain that cogency and coherency, so it use minus eta naught. Now, anyway, so that is not a very big deal. Now, what we can write is that this eta naught is equal to Cf, where your like it is the field that is proportional to this field current, or you can write it's F naught. Means magnitude wise they are proportional, and if we consider phasor relation, then this one is like sorry, minus eta naught is equal to your, we are having this man minus Kc if not. So what you will get here is that that is very interesting. You will be having a diagram like just a minute. So here you can see that it's a very picture I have again taken from Langstroth for a few things that we should not forget. What is common between the two diagrams is that, as I mentioned, here you can clearly see that now it is a game of magnitude rather than a game of sign, and it is the angle delta that is between V and our E. Now, one thing that is very clear and we should not forget about it is that it's like as we can write correctly, V equal to minus E plus IZS. So basically, if you add these two, you are going to get, now from our description, two slightly different things are there. Like they have utilized this symbol for power factor while we use theta. So this is our theta, and this gentleman, that is the angle between I and IZS, that is not this, rather our case it is gamma. right? So these two are at an angle gamma from our phasor I. So again, this one, that V and this should be like angle between I and is how much? Is gamma, where gamma is tan inverse xs by r. Similarly, the phasor V by Zs and phasor V, their angle difference is also gamma. Correct? Now the case is that if you draw these two, then what remains that if you draw gamma minus Zs, right? So okay, let me write a few equations that will help you to figure it out. Like what we can have here is that, or from that this equation we can write Izs whole square is equal to V square plus Cf square minus 2VCF cos delta, right? So this is like V square plus E square minus 2VE cos delta. Now here, if we consider that here what we are investigating like the previous case, it was power F, power P was held constant, and now we are keeping our excitation, that is F, constant. So if we keep F constant, or means keeping F, or in our case it is E naught, means don't get confused, like there are sudden symbol change. So all what is E for Langsdorff, in our case it is E naught. So if we keep our excitation constant, that implies our E naught is constant. So what you will get, like if you do it, it will give you something very strange. Like if you want to get I square, it will give you V by Z square, this by Z square, then here also by Z square, right? So clearly we can see that for a constant value of F naught, what we can have here is that a triangle whose two sides are constant, because Zs is constant, V is constant, and we are keeping Cs is constant. The only variable is I, and that this delta may vary. That is also a very important thing, and we should not means neglect or overlook this aspect. Like for different value of delta, we can get different current. So what we can do here is that we can draw triangles with one side V by Zs and another side is Cf by Zs, right? So then between them, what we can expect between V and Cf, we can expect that this is the triangle what I was talking about, with one side V by Zs and one side V by Zs, that is constant, and another side Cf by Zs, that is constant. However, this I This is clearly a function of delta. And see the beauty, if you make delta is equal to 0, then V by Zs and Cf by Zs will become collinear, and it is quite the case because your I should be 0 because you are not actually delivering any mechanical power, because we have already proved that if we neglect the armature drop, then our means power is proportional to the power angle delta. It is sine delta. Means P is equal to 3 by VE by X sine delta. So that delta, if you make delta is equal to 0, then obviously the power will become 0. As you have not considered in other losses, your I should also become 0. Right? Now that this will give you this kind of diagram. So now we'll do things where our means what we have concluded, or what conclusion we can draw from these two study, that our armature current so now we'll try to like get them together in a single picture. So now when we try to study these two, briefly let me do one thing, like let me just try to fuse the two circles together, like uh, one is giving us our like armature current of is a function of power, and let me just quickly draw two circles, like one is just a minute. So what is here, like I have already spent near about 15-20 minutes drawing all these diagrams, so I kept it in hold. Now here you can see that we have discussed two type of circles. One is power circle, another one is our like excitation circles. What we can do is that now if we just try to fuse them together, means just try to just do like this. I'm trying this I cannot do in this way, like otherwise you will not get the feeling. Yeah, kind of this kind of things we are trying to do, like yes, it's like that. So if we do that, then means a diagram that is drawn in scale perhaps give you a better feeling, and I'm going to insert that diagram. Yes, so you will get this kind of diagram, and it's very clear from this diagram that what we are having two like two circle. One is center at O, like sorry, not circle center at O, rather that circle center at our this point. See, wait a minute. Yes. So this is our that center, right? Now you see that what we are having here, we can draw our like we are having 2 points, and then like one is just a minute. Yes, just a minute. I got confused because from many books I have to collect the references or a better diagram. This is the point O. What we are supposed to do, we draw means with a radius V by Z is this one, right? With this radius, V and ZS is your so this one and V is your terminal voltage. With this radius, we draw an arc, and that arc intersect the zero power circle. This is the zero power circle at a point B. Now, from that point B, what we have done, we can show you that angle cos AOB. Where is your angle cos AOB? It is like that. Just a minute. Let me look at the point A. Yeah. Okay. So what we are doing here is that from our point O, we draw a radius, that is V by ZS. V is your terminal voltage and ZS is your this guy, that synchronous impedance. So V by ZS, and then let it intersect the zero power circle. This outer circle is zero power circle. Here PD is equal to 0 at a point B. Then what about this angle cos AOB? This cos AOB we can write cos AOB is equal to OB by OA, and this is equal to, see, that whole thing is like we know that a semicircle angle is always 90°. So this much is always 90°. Now this side is V by R, this side is V by ZS. So cos AOB is equal to OB by OA is equal to V by ZS divided by V by R, that is equal to R by ZS. So that this one is what is that R by ZS is basically giving you the cos gamma, right? Therefore this angle AOB is your gamma. See the beauty that we started, we try to combine the two circles, and now we are getting something very exciting, that machine internal angle gamma you can say machine internal angle, that is the angle between that if you draw the impedance triangle of the machine, then it is like gamma. So this angle is gamma. So it's very interesting. Now see that if we now draw a circle at center B with radius E naught by Zs, yes, this is the circle with radius E naught by Zs, then that E naught by Zs, we can draw the locus of current phasor I for that particular given E naught, right? We can draw the phasor of current I for that particular phasor E naught. Just let me clear the picture, then it will become more clearer to you. It's that this is our like for E naught Zs, this is our I. Now see that what is the issue here is very simple, that the intersection between our excitation circle corresponding to a particular value of E naught and PD that locates the position of armature current. Now you can see that for one power circle, try to understand one thing, that on this power circle, on every point, it actually gives you the equal amount of active power, right? But as long as you are moving along this circle, everywhere you are having exactly same amount of power. Now here one thing that is interesting, and with that I am going to conclude here, that for a current we can have two different values, sorry, for a given power, say for this one we can have two different values of current, or in this book they have taken this one where the power is constant at PD1. Now see, for this you can have two different values of current, I1 and I2, right? Now here clearly one thing that is clear from this diagram, that this V by Zs is what? V by Zs is at an angle gamma from your line V or V by R, and this like this I1, let me draw the two, otherwise you will not get it. This is our I1, this is our I2. So we are getting, for a constant excitation E naught and a constant power requirement PD1, we are getting two value of current. Now this if you still are in confusion, then you can also utilize that kind of sine wave curve for our, what I discussed in last lecture, that for delta you can see that you are having two value of delta that gives you same power. Now the question is that which one should we use? One thing that is very clear from this picture, that we can have delta 1, that is for I1, and delta 2 for I2. And if you ask me to draw a corresponding phasor diagram for this, I can show you. Here these two are like for same value of delta, you will have equal power, so that gives you equal power. But Here we must not forget that what is the stability limit. I'll discuss in my next video. Uh, because if I start continuing this one, then it will become video of again the duration will be greater than 1 hour. But here one thing I would like to discuss, that in my next video I'll discuss V curve and O curve of synchronous machine, as well as we'll see condition for unity power factor and also the condition of minimum and maximum excitation. In addition, here one thing is very clear and should not be we should not confuse about it, is that it is like these two are giving us stability limit. What is stability limit, that we will discuss, but in a nutshell what we can say, that stability limit like this angle is gamma. So if our power angle is delta 1 is less than gamma, then it is stable. If delta 2 is greater than gamma, then it is unstable. And from which line the stability limit has to be drawn? The line of stability limit, this line, it is a line that is making an angle gamma with the line V by ZS. So once again, before I close, how we draw it? First we take a line, then draw a vertical line, then we fix a center. This length was the half length was how determined? We determine the zero power circle. The outer and the outermost circle is zero power circle with radius V by 2r. Then the total length of that, the total diameter of the circle is V by r. This is zero power circle, and then we go keep on forming concentric circle. What this concentric circle gives us, that on all the points of this circle, the value of current, whatever we will get, is the value of power is constant. Now what is the physical interpretation of this circle, is that on this circle this gives us a constant power. These circles are known as constant power circle. The circle that is centered at C, constant power circle. But unlike the fact, more you go in this direction, your power will be small, and more you go in means the direction where the radius of the circle shrinks, the power will be high. At center you are having maximum power, that is given by right, and we can show that this power is having efficiency is equal to 50%. Now what we are having here is that then from this line, this point of O, where this is the vertical horizontal line and this is the vertical line V by R, we draw another line with, or we draw an arc, better to say, with radius V by ZS, where ZS is your synchronous machine impedance. So that ZS line that arc intersect this point at B. Now from this point B, we started drawing circles, concentric circles with arc that is E naught by ZS. Now if I ask you about the plane of this diagram, although we are talking everything about current here, there, sorry, means power, sometimes it is excitation. This plane is actually plane of current. This plane is actually plane of current. Now this excitation circle, you can see the radius is E naught by Zs. If you keep on E naught constant, you will get this kind of right. This kind of concentric circle can be drawn from center B with E naught by Zs. However, here the case is quite straightforward. Like if you keep on increasing E naught, means you will move outward. More you move in this direction, your E naught will be high. And accordingly, for a constant E naught and constant P, like here it is our PD1 and E naught, we are getting two value of current. One is I1, another one is I2. So we are getting that for I1 and I2 we are having same power, but then for these two we found that the power angle, this one is for delta 1, another is for delta 2. If this delta 2 is greater than delta gamma, then our system will become an unstable one, right? So now let me conclude.